We will now have a look at the standard signals, discrete time signals, which we will make use of in considering the performance of discrete time systems. Now let us look at the basic discrete time signals. The first signal that we will talk about, the unit impulse. It is also called unit signal or unit sample. Basically, so it is 0 everywhere except when n equals 0. So this is called delta n, that is the symbol that is used for this. It's equal to 1 for n equals 0 for n not equal to 0. So this is just a single sample occurring at n equals 0. This is called a unit impulse, simply called a unit sample or a unit signal. It is the term impulse is used borrowing the terminology from the continuous time signal. It does not mean the value of this at n equals 0 is infinite, it is finite, it is equal to 1. So impulse perhaps is a kind of misnomer, but still we will call it a unit impulse because it corresponds to what we have as a unit impulse in the continuous time system. It is symbolized as delta n, 1 for n equals 0, 0 for n not equal to 0. Now, just like a unit step, we also here in the continuous case, here also we have a unit step symbolized as un. Now here the value of this discrete time signal is 1 right through for all non-negative n, 0, 1, 2, etc., and 0 for negative values of n, like that. So un can be written as 1 for n greater than or equal to 0, 0 for n less than 0. So in contrast to the continuous time case, here at n equals 0 we have a definite value which is equal to 1. In the case of a continuous time case, at t equals 0, as a unit step is concerned, we can take it as 0 or 1 or half or whatever it is. It can be left ambiguous. But as far as the unit step in a discrete time case is concerned, the value is definite and it is equal to 1. So this value is equal to 1. Here also this is equal to 1. Now similarly, you can have a unit ramp. It is symbolized as Rn equals n for n greater than or equal to 0, 0 for negative values of n. So that would be 0 everywhere, but here it will be 0 like this, 1, 2, 3, 4, etc. up to. So at 1 it is equal to 1, at 2 it is equal to 2, and so on and so forth. So that is what is called a unit ramp, which is somewhat similar to what we have in the case of continuous time system, except in the continuous time as a function of t it takes off like this, but here the values of the samples increase in proportion to n. We can also have an exponential signal. E to the power of alpha n. So you have something like the exponentially increasing, like this, e to the power of alpha n. Now on the other hand, if I have e to the power of alpha n times u of n, that means this is multiplied by a unit step, that means all the samples are cut off and you are having only this portion. That is obvious. If you multiply e to the power of alpha n by un, that means the negative samples for negative values of n are just removed. They will be equal to 0, of course. Similarly, you can have a sinusoid. You can have sine omega, n omega n or n omega, which will be, in a general case, this is the envelope, the samples will be like this. All the samples will fall on an envelope which is a sine wave. Similarly, if you have cos n omega, it will be a similar situation, but this will be now a cosine curve. So the samples will be again discrete, but the tips of all those samples will follow a sine wave or a cosine wave as the case may be. Sine omega n omega or omega n, can write maybe better to call it n omega, sine n omega and cos n omega are sinusoidal signals. Again, if you take sine n omega multiplied by u of n, this portion will be cut off. Cos n omega multiplied by u of n, this portion will be cut off. Now these are the basic type of discrete time signals that we would like to use. From this we can build up other signals, for example e to the power of alpha n, sine n omega, that type of signals, multiplication of these two, all those things can be produced.